Hi, we are now in the fourth session of this course, and in this session, the topic will be more on system response. Okay, we have already discussed the first three topics in the previous weeks. We now move to the next stop. We are going to discuss response and stability of systems. As an outcome of this topic, then at the end of this week, you should be able to identify poles and zeros from systems, and you should be able also to assess the stability of dynamic systems. So, when we are given a system, a dynamic system, as normally we can also represent it in a differential equation form, in transfer function form, or also in a block diagram form, as you can see in this slide. The first question that might appear in our head is how to assess the performance of the system. You have different system. Each system might behave differently. Let's say if you have a DC motor, the performance of one DC motor might be different to the other DC motor. The performance that I'm referring to here is the dynamic performance, of course. And then if you are going to design a controller for such a system, the controller that you are going to design is restricted to the system that you want to control. So, assessing the performance of the system, understanding the behavior of the system will help you to understand how far, how deep you have to design the controller for the system. By understanding the system, you will be also able to assess how good your system with a controller that you design. So this is a few things that we are going to target in this week. Let me pop again the one of the slide that we have already seen in the first week when I introduced the dynamic system to you. So as I have already mentioned last time, that dynamic system is always represented by a differential equation to correlate the output and input here. And the main feature that differentiate dynamic system to static system is that the output of a dynamic system is varying in time, even though you are giving a constant input. Okay, now how do we assess the performance of a system? The behavior of the system will be different depending on the input. Let's say if you are giving a constant input, the output will be different than if you are giving a sinusoidal input. So to which input that we have to assess the system? Do we have to take a look on the response of constant input? Do we have to take a look on the response of sinusoidal input when you are going to assess the performance of the system? Or do we have to take a look on the response of any arbitrary input? How many inputs there might be that you need to use to assess the performance of the system? There are many, many types of input. To answer that question, we will take a look on the unique property of a dynamic system, which is called superposition principle. So when we are talking about dynamic system, any dynamic systems, any to linear dynamic system to be precise, always hold superposition principle. What is superposition principle? Let's consider a system with a transfer function GS. Now let's assume we give an input UI to the system with a transfer function GS. And then the output of this system will be Y1. Okay. Now let's take a second case to the same system with the same transfer function GS. We give an input U2 and apparently the output is Y2. If we give to the same system again now another input where the input is the superposition of U1 and U2, so we give an input of U1 plus U2 to the system, to the same system, apparently the output is just simply y1 plus y2. The output will be just a superposition of the first output and the second output. This is what we call as a superposition principle to the system. But this superposition principle also holds to signal. What do I mean by that? So let's consider arbitrary input, as you can see in the first plot here. If you look at it carefully, this signal looks like a signal with arbitrary shape. It's like a random signal. But based on this superposition principle, it says that any signal can be decomposed into a combination of simple signals. Those simple signal might be a linear signal, the first one, or a constant signal, a step signal, T2, or it is also impulse signal, or it can be a parabolic signal. So if you combine these simple signals accordingly in such a way, you will be able to approximate any arbitrary signal of this. Okay. So based on these two superposition principles, we can have an answer to our first question on how to assess a performance of a dynamic system. In this slide, I give an illustration of some typical simple signals. So you have the first one is a step function. Step function basically is just a constant function. The second one is a ramp. Ramp is a linear function in time. The third one is parabolic function, where the function appears as a parabolic function to the time. The fourth one is impulse function. What is impulse? Impulse is just a function that has a value only at one specific time. So you have a pulse there. And the last simple function is the sinusoidal function. So these are the, let's say, simple functions that you can use to construct any arbitrary signal. And based on the superposition principle that we just discussed, that any arbitrary signal can be decomposed into combination of these simple signals. So we can conclude that when you are going to assess the performance of a dynamic system, you don't have to test it with a ton number of test signal. You don't have to test it with any arbitrary signals. You don't have to test it with a random signal. You just need to test it with these simple signals. And then let's call these simple signals as the test signals. So in short, I can say that if you are going to assess a performance of a dynamic system, you just need to use these five test signals.